Good morning, class, and welcome to Chapter 5, Part 2. Please make sure you have your pre-printed notes with you, a pen or pencil, your periodic table, and any scratch paper. So let's do a little bit of review. Alpha, beta, and gamma emissions all have different abilities to penetrate matter. The alpha particle was the largest of all the particles that we studied. Remember that it is the size of a helium nucleus, so it has a mass of 4 with 2 protons and 2 neutrons. This large particle is easily stopped by matter, such as clothing, although it may impart a significant amount of energy to the matter it contacts, meaning if it smacks into you, it may impart some energy, but the particle itself will not penetrate your skin. Beta particles might penetrate a little bit into matter, such as your skin, perhaps a few centimeters at most. But you may remember that gamma rays are super high energy. These can penetrate deeply into matter, including through the human body, and they impart a large amount of energy into the surrounding matter. Remember that gamma rays have no charge on their own. However, if they strike an atom or a molecule, what they're passing through, they can convert that atom or molecule into an ion by knocking an electron out of orbit. So to protect ourselves from radiation, if you're dealing with alpha particles, paper and clothing will easily block them. If you're dealing with beta particles, a heavier lab coat or gloves is fine. But if you're dealing with gamma rays, you need dense shielding such as lead or concrete, which is why when you go to the dentist to have x-rays, they always put a lead shield on you to protect you. So if you're working in an environment where radioactive materials are present, you want to limit your exposure by minimizing the amount of time you spend near a radioactive source and by increasing your distance from the source. Now, let's go back and do some more review. In the nuclear equation for alpha decay, the mass number of the new nucleus decreases by 4 and its atomic number decreases by 2. So let's complete the following nuclear equation for the decay of americium-241. Again, our new element is going to have a mass that is smaller by 4. Smaller by 4. So 241 minus 4 is 237. That doesn't tell us what our new element is because our new element is determined solely by the number of protons, not the mass. We have lost 2 protons. Again, remember that an alpha particle is 2 protons and 2 neutrons. So we have lost a mass of 4, and we have lost 2 protons. So we went from 95 protons down to 93. If we look at our periodic table, the element with 93 protons is, where is it? NP, Neptunium. NP, Neptunium. Okay. Again, remembering that on the left and the right, we must be balanced. We have a 241 on the left. On the right, we have 237 plus 4, which is 241. On the left, we have 95. On the right, we have 93 plus 2, which is 95. So we're balanced. Okay. Let's try another one. Let's review beta particle, right, which is an electron emitted from the nucleus. That is a neutron being converted into a proton. So we have a neutron becoming a proton. Remember that the mass of the element is not changing, right? We aren't losing anything from the mass because a neutron and a proton weigh the same. That's indicated by this 0 here. So our mass is still 42. However, this 19 here, right, a neutron has become a proton. So we now have 1 more proton. We went from 19 to 20. If we look at our periodic table, the element with 20 protons is calcium. So our new element is calcium. Again, we had 42 on the left, 42 on the right. 19 on the left, 20 minus 1 is 19. So we are balanced. Let's try another example. Let's write the nuclear equation for the beta decay of, let's see here, 60 CO is cobalt. So we have 60 CO. If we look at our periodic table, we will see that cobalt has 27 protons. Okay. We are doing beta decay. Remember that the symbol for a beta particle is a 0 and a negative 1 with an E. Again, left and right must be equal. Okay, left and right must be equal. We are not changing the mass, so the mass stays at 60. Okay. We are, however, changing the number of protons. We have a neutron turning into a proton, so we now have one more proton. So we went from 27 to 28. And again, the protons define the element. So if we look at our periodic table, we will see that the element with 28 protons is nickel. 60 on the left, 60 on the right. 27 on the left, 28 minus 1 is 27. So 27 on the left, 27 on the right. We're balanced. Again, just to review, in a positron emission, a proton is converted into a neutron. So now instead of a neutron being converted into a proton, we have a proton being converted into a neutron, and we are ejecting a positron. The mass number still stays the same, but now our atomic number, which is the number of protons, decreases by 1. Decreases by 1. Gamma radiation is just energy emitted from the unstable nucleus. Okay? Gamma radiation, again, not changing mass, not changing charge. So the element stays the same. Okay, so radioactive isotopes can be produced when a stable nucleus is turned into a radioactive nucleus by smacking it with a small particle. We call this transmutation. So boron is a perfectly happy stable nucleus. If you come along and whack it with an alpha particle, it becomes a radioactive nucleus. Just like before, we must be equal on both sides. So here we have a 4 and a 10 for 14. On the right, we have a 13 and a 1 for 14. Mass, we have a 2, protons. We have a 2 and a 5 for 7. Over here, we have a 7 and a 0 for 7. So just like before, everybody has to balance. Okay? Let's try one of these. So let's write the balanced nuclear equation for the bombardment of nickel-58 by a proton, which produces a radioactive isotope and an alpha particle. So they're, in words, giving you the first half. Nickel-58, Ni-58. If we look at our periodic table for the element nickel, we will see that there are 28 protons. The proton, which is from the previous lesson, is H, which stands actually for hydrogen, which has 1 proton and no neutrons, right? A mass of 1, a charge of 1. Okay, that was given in the question. We were also told it produces a radioactive isotope, which we are trying to find, and an alpha particle. Okay? So you were given 3 of the 4 pieces, and we want to find the 4th piece. We are going to use the law of conservation of matter to determine what was the new element created. On the left, we have a 1 and a 58 for a total of 59. On the right, we have a 4. What plus 4 will give you 59? Well, if we subtract 4 from both sides, we will see that 55. 55 plus 4 will give you 59. But that does not tell us what the element is. Remember that the element is determined by the number of protons. So we have 28 protons plus 1 for 29 protons on the left. On the right, we have 2 protons. So what plus 2 will give us 29? If we subtract 2 from both sides, we get 27. 27 plus 2 is 29. So our new element has 27 protons. Again, the number of protons is our defining characteristic. If we look at our periodic table, we will see that the element with 27 protons is cobalt. So our daughter isotope, our new isotope, is cobalt. Let's try another one. What radioactive isotope is produced when a neutron bombards 98 technetium, releasing an alpha particle? So we're given technetium, Tc, 98 is its mass. How many protons does technetium have? Looking at our periodic table, we see that there are 43. We're also given a neutron. A neutron has a mass of 1, a charge of 0, and a symbol N. So 1 neutron plus technetium releases, an alpha particle, which is a 4, a 2, and a helium. Okay. On the left-hand side of the equation, we have 98 plus 1 is 99. On the right-hand side of the equation, we have 4. Remember that both sides of the equation must be equal. So 4 plus what would give you 99? 4 plus 95 would give you 99. On the bottom, you have a 0 and a 43. So you have 43 on the left, 2 on the right. 2 plus what would give you 43? Well, 2 plus 41. Now, if we look at our periodic table, what element has an atomic number of 41? Well, element 41 is Nb, or niobium. Nb. So the element that belongs here is 9541 Nb, niobium. Okay, we have lots of different units for measuring radiation activity, including curies, which is the number of disintegrations that occur in 1 second for 1 gram of radium. This is approximately equal to 3.7 times 10 to the 10 disintegrations per second. A disintegration is just describing the decay of that particular radioactive atom. We also have a becquerel, the SI unit of radiation activity, which is just 1 disintegration per second. We have something called rad, or radiation absorbed dose. This measures the amount of radiation absorbed by a gram of material, such as body tissues. And then we have REM, the radiation equivalent in humans. This is a measure of the biological effects of different kinds of radiation. It measures alpha particles, which do not penetrate the skin. However, if they were to somehow enter the body, extensive damage could occur. High energy radiation, which causes more damage than alpha particles and includes your beta particles, your positrons, and neutrons that travel into tissue. And then finally, gamma rays, which are the most damaging because they travel a long way through body tissue. In order to determine the equivalent dose, or REM dose, the absorbed dose, rad, is multiplied by a factor that adjusts for biological damage caused by a particular form of radiation. So again, the biological damage, the REM, is equal to the absorbed dose, the rad, times a factor. The less damage, the higher the number. So for example, alpha particles, the factor is 20. Beta and gamma radiation, some of the most damaging, the factor is 1. In the middle, you have your high energy protons and neutrons, and that factor is about 10. The average person in the United States is exposed to about 360 millirem of radiation per year. Exposure to radiation happens to all of us every day, from naturally occurring isotopes in buildings, in the air around you, in the food and water that you eat. Pretty much everybody is exposed to some form of radiation, just not generally in enough levels to be dangerous. Some sources of naturally occurring isotopes are potassium-40 in potassium-containing foods like bananas, cosmic radiation from the sun. Generally speaking, the larger the dose of radiation you receive all at once, the greater the effect on the body. So exposure to tiny little amounts on a daily basis, such as we get, isn't generally dangerous. Exposure to a radiation of 500 rem is expected to cause death in 50% of the people receiving this dose. Again, remember that the average person in the United States is exposed to 360 millirem. Remember that there are 1,000 millirems in 1 rem. So 500 rem would cause death in 50% of the people receiving the dose. We call this the lethal dose for 1/2 the population, or LD50. LD50 is the amount of anything that would be lethal to 50% of the people receiving it. And the last thing we're going to talk about this chapter is the half-life. The half-life of a radioisotope is the time for the radiation level to decay to 1/2 the original value. So if you started out with 4 milligrams of a radioactive substance, the half-life is how long it would take until only 2 milligrams of the substance is still undecayed. Okay? So for example, in this example that you show here, you can see kind of a picture. 13153 iodine has a half-life 8 days. 1/2 of the sample decays every 8 days. So after 8 days, half of your sample is still your 13153 iodine. The other half is your 13154 xenon. That's what it has decayed into. After 2 half-lives. Now, if 1 half-life is 8 days, 2 half-lives would be 16 days. After 16 days, 1/4 of your original sample is left. The other 3/4 is now a new element, xenon. After your 3rd half-life, now you had 8 days the first time, right? 16 days, then 24 days, right? Every 8 days, a new half-life passes. So after 24 days, now 12.5% is left, right? The rest is the new element, xenon. So let's try an example. Example 11 says the half-life of fluorine 20 is 11 seconds. If a sample initially contains 5 grams of fluorine 20, how much remains after 44 seconds? Well, the first thing you need to determine is how many half-lives have passed. So after 1 half-life, 11 seconds have passed. After 22 seconds, you have 2 half-lives. After 33 seconds, that's 3 half-lives. After 44 seconds, that is 4 half-lives. So 4 half-lives have passed, which means that the amount of sample remaining, if we started with 5 grams, after 1 half-life, we would have 2.5. After 2 half-lives, we would have 1.25. 1.25. After 3 half-lives, we would have 0.625. And then finally, after the 4th half-life, we would have 0.3125. And that was grams. Right? All of the rest of the sample is now whatever the fluorine 20 has decayed into. Let's try another one. The radioisotope strontium-90 has a half-life of 38.1 years, so a much longer half-life here. If a sample contains 36 milligrams of strontium-90, how many milligrams remain after 152.4 years? So step 1 is to determine how many half-lives have passed. So 152.4 divided by 38.1, because each half-life is 38.1 years, we get 4. 4 half-lives have passed. So after the first half-life, we have 18 milligrams left. After the second half-life, we have 9. After the third half-life, we have 4.5. And finally, after the 4th half-life, we have 2.25 milligrams left. So again, when doing a half-life problem, you want to look at how many half-lives have passed. And then you divide the sample in 2 by the number of half-lives that have passed. Do not divide the sample simply by 8. Okay? Dividing the sample by 8 would give you 4.5. Right? This is 2 times 2 times 2 times 2. All right, two final examples. Carbon-14 was used to determine the age of the Dead Sea Scrolls. Hopefully you've all heard of those. If the Dead Sea Scrolls were determined to be 2,000 years old, and the half-life of carbon-14 is 5,730 years, what fraction of a half-life has passed? So fraction, obviously we're going to have a numerator and a denominator. We want to know fraction of a half-life. The half-life is 5,730. 2,000 years is less than that. So we know that our fraction is going to be less than 1. Right? So we have 5,730 years. Only 2,000 years have passed. If we turn this into a decimal, 2,000 divided by 5,730, we can see that slightly less than half, actually closer to a third, right? 0.350, so close to a third. 0.350 half-lives have passed. One more. The half-life of I-123 is 13 hours. How much of a 64 milligram sample is left after 26 hours? So 26 divided by 13 tells us that 2 half-lives have passed. So 64 divided by 2 tells us that there are 32 milligrams left after 13 hours. After another 13 hours should be 16 milligrams of iodine-123 left. Okay. This concludes Chapter 5, Part 2. Thank you so much for listening, and I look forward to seeing you for Chapter 6, Part 1.